Good evening. So far, we have studied the compressible flow. The part of which that we have studied are the stagnation properties, the ratios of the stagnation and the static properties, and the sonic velocity. And we also have determined one, we have also defined one property of the flow called the Mach number, which is the ratio of the velocity of the flow to the velocity of sound in the medium of the flow at that particular temperature where the flow is taking place, at which the flow is taking place. So, with that, now we will move to the isentropic. Now, with that, we will move to the topic isentropic flow in one dimension. Now, actually, the background for this study is that most of the compressible flow or many compressible flows having one dimensional in nature. Many compressible flows are one dimensional in nature, like the flow through a nozzle, that is the flow through a steam nozzle, or the flow through the passage of blade in a steam turbine. So all these are mostly one dimensional and isentropic. So that is the motivation for studying one dimensional isentropic flow. So one-dimensional isentropic flow we will study next. Now, for that, what we will do is basically we will define or we will show you certain conduits for the flow. So here you see that there are certain geometries. So this is the direction of flow that you can see. So this is the direction of flow from left to right. And in this direction, the area is decreasing. So that kind of geometry or that kind of device is called a converging duct. Initially, we will call it a duct. We will not mention the name as nozzle or anything else. Initially, we would like to call it as duct. So for this, the area is decreasing, so it will be called as converging duct. And if the area increases, then we will call it a diverging duct. So it can be like, so it can be like a diverging duct can be like in the direction of the flow, the area is increasing. So it is a diverging duct. And if we have this kind of geometry where initially the area decreases and then it increases, it will be called a converging diverging duct. So here, as we can see that as the area gradually decreases and then after that it increases, there is a minimum area of cross section that will be called the throat of the duct. So now we will try to analyze for certain geometries like these, that what will be the relation between the temperature, pressure, density, Mach number, velocity, etc. with the area. So how these quantities like temperature, pressure, density, Mach number, velocity, etc. changes with area, uh, that is the target for this flow. So we will study those variations in detail. Now, so okay. Now initially, another thing that I would like to mention here is that this kind of converging diverging duct is also called a D-level nozzle. So converging, let us show it, converging diverging duct. So this part is converging initially. And this part it is diverging. This kind of nozzle for compressible flow, we call it a D-level nozzle. Due to the fact that this is designed by a Swedish engineer Carl G.V. D-level. Okay, next, what we will try to see the variation of the velocity with the flow area. First, we will try to see that. So for that, we will now this derivation or this kind of analysis basically is for any variation of area. So it is irrespective of the variation of area. So we are not focusing on a particular type of variation, either it is converging or diverging or converging diverging. So that will be general, and after that we will analyze according to the area variation whether it is converging or diverging or converging diverging. There is a particular case, so we will study that part after this general derivation. So initially what we will do is we will go for mass conservation. So this analysis will start with mass conservation. That you see that our target is what? Our target is to understand the variation of fluid velocity with the flow area. So here we see that this is a variation of fluid velocity and flow area. So here it could be guessed that we need to study the uh, mass conservation, because in the mass conservation we have the flow velocity and area both. So what is that mass conservation at any section? If we try to understand the mass conservation at any section in a duct, so mass conservation or mass flow rate is equal to basically rho A into V. So rho into A into V. So rho is the density. Now these quantities rho A, V all are actually varying. All are actually varying along the cross section. So I am writing mass conservation at or mass flow rate at a particular section. We can take mass conservation at a particular section. So that can be at any section, like this one. It can be here, it can be here, it can be here, anywhere. And accordingly, the quantities, that is mass flow rate, is a product of density into area into velocity. So density at this section, area at this section, and average velocity at this section. So that is the part, that is the concept of this analysis. Okay. So therefore rho is equal to density. So I can write here mass flow rate at any section. Okay. And density, area of cross section, and velocity at that cross section. That is common mass flow rate equation or mass flow rate expression. Next, now, since we know that this mass flow rate is constant and the individual parameters are varying, you see that rho is generally, rho will vary, is a compressible flow, I mentioned. And for compressible flow, I told that the density variation cannot be neglected. It is significant. And also we see that there is area variation. And also velocity will vary. Therefore, these quantities on the right hand side, all quantities are varying. But on the left hand side, mass flow rate, which is a conserved property. Therefore, conserved quantity. So we can write, if we go for differentiating, then we can write that if we differentiate, then dm dot say is equal to d rho multiplied by a into v plus rho into dA into v plus rho a into dv. What I am doing? For a differentiation of a product, the rule is that one quantity will be unchanged and the other quantity will undergo the differentiation. So that is simple, the differentiation of product that I have done. So here you see that rho underwent the differentiation and AV as it is remain fixed. After that, rho and V kept fixed and A underwent the differentiation. And at the third term, rho into A remained fixed and V underwent the differentiation. Okay. Next, what we can do is we can now divide both sides by this quantity. Now, as this is constant, so this will be 0. So if I divide both sides with this, so it will be basically d rho AV product of d rho and AV rho dA multiplied by V plus rho A multiplied by dV divided by rho A V. So after that, it will be 0 is equal to now here you see that rho AV and AV, this AV part will cancel. Therefore, it will be the first term will be rho d rho divided by rho first term because this rho A AV and this AV will cancel. After that, it will be rho and V will cancel. So A will remain. So it will be dA by A. And the third term, you see that rho A will cancel and V will remain. So it will be dV by V. Okay. So this is one important equation. So we'll mark it, highlight it. We will call it, say, equation 1. So it is a differential equation between the quantities such as density, area, and velocity. Next, we will go for analyzing the. Hello, 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 hello. কিছু বলছো কেউ? হ্যালো, কারো কিছু সমস্যা হচ্ছে? কি হলো বুঝতে পারছি না। হ্যালো। ওকে ওকে, আচ্ছা আচ্ছা, আমি অ্যাকচুয়ালি মাইকটা অফ করে ছিলাম, ভুলে গেছি, বুঝতে পারিনি। আর একটু আগে বলবে তো, আমি তো অ্যাকচুয়ালি ক্লাস চালিয়ে যাচ্ছি। ঠিক আছে ঠিক আছে, আমি বুঝতে পারিনি। ওকে ওকে। ওকে, আচ্ছা। So far we have discussed the variation of, we have started discussing on the variation of fluid velocity with the flow area. So for that, what we have considered that the conservation of mass or the mass flow rate, which is constant. So after differentiation, the left hand side will become zero, but the right hand side will be containing the variation of density, variation of area, and variation of velocity. As for the compressible flow, all quantities will vary. Generally, all the quantities will vary. Therefore, this will be the differential equation of, or the relation, a differential relation between density, area, and velocity. So we have discussed in the today's class up to this. Okay. Next, we will go for analyzing the energy. So we will write the energy balance first. Next, so for this case, there will be, that means the flow energy and the kinetic energy will be basically interchanged or interconverted. The flow energy and the kinetic energy will be converted between themselves. And the potential energy change is considered negligible. So we can write, so it will be basically Okay. So for this, we can write this. Okay. Next, our target is to calculate the variation with the area of the velocity. So what should I do here? So for this, what should be done? So it can be proved. Okay. This can be proved. Then how this comes for the isentropic flow, that can be proved. So as we know, for isentropic flow through a duct without heat transfer and work done, so H plus V square by 2 is equal to constant. That we have seen in the first class. So that is for Q is equal to 0, W is equal to 0, and delta PE negligible. Now, if we differentiate this, it will be dH plus V dV is equal to 0. Okay. Next, from the TDS relation, we know what is that TDS relation? TDS is equal to dH minus VdP, that we know. Second TDS relation. So therefore, dH is equal to TDS minus VdP. Again, here it is isentropic flow. So it is 0 for isentropic flow. Therefore, dH is equal to VdP. Again, we know that V is equal to 1 by rho. Therefore, dP by rho. So therefore, I can write here, it is dP by rho plus V dV is equal to 0. So that we can see, that we are using here. Okay. So that is the energy balance for the isentropic flow with no heat transfer, no work done, and no change in potential energy. Okay. Now this, you can see that this is kind of the Bernoulli equation, the differential form of the Bernoulli equation. Okay. Only thing is that potential energy change is considered negligible. The potential energy is 0 here. The change in potential energy is 0. So that term is dropped. Otherwise, it is the Bernoulli equation. Okay. Now, therefore, if okay, I have just mentioned it that I started discussing on this isentropic flow along one dimensional condition, that is one dimensional isentropic flow. So the flow is taking place in one dimension, and the motivation I told that most of the flow uh, that we come across in the compressible flow domain are basically one dimensional, like say flow through a nozzle, or that is flow through a steam nozzle, or flow between the blade passage in a steam turbine. All these are mostly isentropic one dimensional flow. So that is the motivation for studying this topic in detail. And here we are trying to understand the variation of different quantities like pressure, temperature, density, area, Mach number. That means the density, pressure, temperature, Mach number, velocity, etc. with area. So how these quantities vary with area, that is the objective of this study or analysis. So we started with the mass conservation, and we have got one differential equation here. Okay, so this is equation 1. Again, we analyze the energy conservation for the isentropic flow, and we have got this. So that is one dimension for isentropic flow, the energy conservation with no potential energy change. So now we will relate the area with this. Now, you see that if we combine these two, what we can get? You see that uh, you have dV, V dV, and dP by rho here. So if we try to combine these two, okay, this is equation 2. If we combine equations 1 and 2, so we will basically, you see that we will basically eliminate this dV term. Okay, that is we are going to do. So from this equation, we will calculate dV, and we will basically replace here. That is the thing that we will do. So from equation 2, what is dV? dV, what is that? dV is equal to minus dP by rho V. Okay. So this is energy conservation. This is one important relation that we will refer. From this relation, you see that we can understand easily that if velocity increases, always pressure will drop, pressure will decrease. So this is one important, very important relation that gives us a good insight that always if there is a pressure drop, velocity will increase, or the vice versa. That is, if the velocity decreases, then pressure will increase. Or if the pressure decreases, velocity will increase, or if the pressure increases, the velocity will decrease. That is always going to happen. Whatever be the area, means whatever be the variation of area. Here we see that there is no question of area, or there is no point of area. We are not getting any issue of area here. So it is always true that if the pressure increases, the velocity will decrease. Okay. Next. So that is always true, that you have to understand. Next. Now we will put it here. So here we can write. Is it clear?
Yes, sir.
Yes. So that is always true. Whatever be the variation of area, whether it is converging duct, diverging duct, whatever be that, the this thing is always true, that if the pressure increases, velocity will decrease. If the pressure decreases, velocity will increase. This is always true. Okay. Next. Therefore, what is dV by V? dV by V is equal to, therefore, minus dP by rho V square. Simply, I have divided by V on both the sides. So it is this. Now I will put it here in equation 1. So therefore, it implies that uh, del rho by rho, d rho by rho, d rho by rho plus dA by A minus dP by rho V square is equal to 0. Therefore, dA by A is equal to dP by rho V square minus d rho by rho. Therefore, we can write that dA by A is equal to dP by rho V square minus, this will be d rho dP, because I have taken this dP out, so it will be d rho dP. Okay. So this is also one important relation. This is equation 3. Okay. Next, what we have seen, it is isentropic flow. One thing we have already considered, that this is isentropic flow. Therefore, this quantity is basically a partial derivative del rho del P at constant S. Because it is isentropic, so it is constant S. And we know that del P del rho at constant S is what? Is the velocity of sound. The velocity of sound square. So this is the square of the velocity of sound that we have done, and that we have seen in one of our earlier class. You see, c square, this one, c square is equal to this one, and this is equal to del P del rho S. So this is equal to C square basically. So that we have seen in one of our earlier class. Therefore, this is C square. Therefore, we can put it here. Therefore, dA by A is equal to dP by rho 1 by V square minus 1 by C square. Okay. Next, we can take this V out here so that here there will be V square. So that here there will be V square and we will get a quantity that is Mach number. Okay. Therefore, now we will write dA by A is equal to dP by rho V square. It will be 1 minus V square by C square. And we know that V by C is equal to Mach number. So V square by C square is equal to Mach number square. dA therefore dA by A is equal to dP by rho V square 1 minus Mach number square. This is one important relation. So this is the equation 4. Okay. This is equation 4. So from this equation, what we understand, that is to be seen first. Now here you see that the left hand side, it is dA by A. A is always positive, but dA can be positive or negative or 0. So if dA is negative, that means area is decreasing, that means it is converging. If dA is positive, then area is increasing, that is the duct is diverging. And if dA is 0, that means there is no change in area. So it is called the throat of the duct. Now, on the right hand side, let us see. So Mach number is there. So you see that this quantity in the denominator, it is always positive. Rho V square is always positive. But dP can be positive or negative. And what about this quantity? 1 minus Ma square. So this quantity is positive if Mach number is less than 1. What is that called? Mach number less than 1, that is called subsonic flow. Mach number less than 1, it is called subsonic flow that we have seen in one of our earlier classes. We have seen just this one. You see, Mach number less than 1 is called subsonic flow. So, and Mach number greater than 1 is called supersonic flow. So that means this quantity 1 minus ma square is positive if ma is less than 1, that is subsonic flow. That means what? For a subsonic flow, this is positive, and therefore, if the area decreases, that means for a subsonic flow, if area decreases, what is that? That means dA is negative. Therefore, what will happen to dP? So this is positive, you see that this is positive for a subsonic flow. Now, if dA is negative, that must be negative because dA depends on the product of dP and this quantity. So this is positive for subsonic flow and this is always positive. So dA, if it is negative, then dP must be negative. So if area decreases, dA is negative and therefore dP is positive. Now, if dP is positive, what about dV? We have just mentioned that if dP is positive, dV is negative. Therefore, and dV is negative. Is it clear? First observation, is it clear?
So,
So that means what? We have observed the first thing that if it wait করো আমি চার্জটা শেষ হয়ে গেছে The first observation is that for a subsonic flow, if area decreases, then pressure will increase and velocity will decrease. So now let us draw that geometry. Now we are first time we are drawing the geometry. So far we were mathematically analyzing. Now we will draw the geometry. Okay. So area is increasing. So it will be like this. Area is increasing. Now, Therefore, you see that in this direction flow is taking place. And area is increased. So for this, dA is positive. And this is called a diverging duct. What happens? That means it is subsonic flow. Subsonic flow, that means MA is less than 1. If area increases, then velocity will, first we write pressure will increase and velocity will decrease. Okay, now if the velocity decreases, we call it as diffuser. We call this duct a diffuser. So this duct we call a subsonic diffuser. Subsonic flow and the velocity is decreasing, so we call it a subsonic diffuser. Now the opposite thing will happen if the area decreases. That means what? If area decreases, what will happen? The opposite thing will happen. Simply, you see that if area decreases, that means dA is negative, and this quantity is always positive for subsonic flow. Therefore, if dA is negative, then dP is also negative. And if dP is negative, dV will be positive. Clear? Clear or not? হ্যালো,
স্যার এখনো পর্যন্ত ক্লিয়ার হয়নি স্যার।
ক্লিয়ার হয়নি? তাহলে তো সেটা বলতে হবে, পরিষ্কার বুঝতে হবে জিনিসটা। দেখো, if you see the relations that this is dependent on area, so this depends on area and Mach number. That means area variation is there, and also this relation depends on Mach number. That means there will be different criteria. That means it can be subsonic flow if Mach number is less than 1. If Mach number is greater than 1, then it will be supersonic flow, like that. If area decreases, then it will be a converging duct. If area increases, then it will be a diverging duct. That means on this relation, we will apply different cases for Mach number less than 1, for Mach number greater than 1, for area dA positive, dA negative. So we will basically get 4 cases, isn't it? 4 cases we will get. One thing is Mach number less than 1, Mach number greater than 1. So 2 cases. Again, area less than 1, area greater than 1. So again 2 cases. That means there is a combination of 4 cases. Now, therefore, we will get different variations. So how the pressure will vary with area, that we will understand. But you see that depends. That means how the pressure will vary with area, or how the velocity will vary with area, that depends on the subsonic flow or supersonic flow. Because in this relation you have area variation, then the Mach number dependence and the pressure variation. But you see that this relation is always true. This relation, it does not depend on whether it is subsonic flow or supersonic flow. Do you see that there any dependence on Mach number here?
No, sir.
No. That means what? Here dV will always increase if dP is decreasing. That means if pressure decreases, velocity will always increase, whether it is subsonic flow, supersonic flow, whether it is converging duct, diverging duct, whatever. That means if pressure decreases in some way, then velocity will increase. Always. That is always true. That comes from the energy conservation equation, and this is always true for isentropic flow. Okay. So that
Yes.
understanding must be there. That must be crystal clear. That if pressure decreases, velocity will increase, whatever be the situation, whatever be the case. Pressure variation and velocity variation, they will be always opposite. Okay, is it clear? That should be the first thing that you have to understand.
Yes, sir.
Okay.
sir, मुझे से sir.
Clear though?
हाँ sir, ऐसा मुझे.
Okay. Next, what we are understanding, what we are trying to understand, mass conservation. From the mass conservation, we have got this relation. Next, we have put this part in the mass conservation and we have got this relation. First, so what is this? This is the area variation with pressure and Mach number. Now there will be 4 cases. So now we are actually trying to understand those 4 cases. The first case is subsonic flow and area is decreasing. That means Mach number less than 1 and dA is positive. This is case 1. Next, what we are trying to see? Okay, is this case clear? Simply you try to see. Mach number is less than 1. So 1 minus Mach number square is always positive.
Yes, sir.
Okay. Next, if dA, next we are trying to control this. So first we fix the flow. That is Mach number is less than 1. That means what? You see that dA is a product of 2 terms. One is dP, another is 1 minus ma square. Other quantities are always positive. You see that area, this is always positive. Rho v square is always positive. Okay. Now, if 1 minus ma square is positive, yeah, and dA is positive, therefore dP is also positive.
Yes,
Simple algebra.
Yes, sir.
Clear? So now 1 minus ma square, ma square or ma is less than 1. What is the meaning of that? It is subsonic flow. This is the definition of subsonic flow. Okay. That means 1 minus ma square is positive means it is subsonic flow. So for a subsonic flow, now area is decreasing. So it is converging, diverging duct. Area is increasing, so it is diverging duct. Therefore, for a subsonic flow and the diverging duct, what will happen? Velocity will decrease and pressure will increase. Is it clear?
Yes, sir.
Ekdom clear?
Yes, sir. Yeah.
Okay. It up step by step. So what we are fixing? First, we are fixing this quantity 1 minus ma square. So once it is fixed, that means we have fixed for subsonic flow. So this is fixed. Next, we are manipulating area. That means area increases or decreases. Now, if area increases, this is diverging. If area decreases, then it is converging. Okay. Now, since this is positive for subsonic flow. Now, whatever be the whatever be the sign of dA, that will be the sign of dP,
Yes, sir.
isn't it? Isn't it?
Yes, sir.
Okay. Okay. তারপরে analysis. Next onward analysis are very straightforward. Same thing we will copy. Okay. So now we will go for the case 2. So this is a case 1. Now case 2, area decreases. Area decreases. So we will take a case where area decreases. Okay, we can take it here. Area decreases. area decreases. So here you have one section. Here you have another section. Okay. Next. So next is subsonic case. Again, subsonic flow. Subsonic flow. Case 2. This is case 1. Case 2. What is that? Subsonic flow. Yes. Subsonic flow means MA is less than 1.
Wow.
MA is less than 1. That means MA is less than 1. That implies that implies 1 minus MA square is positive. So therefore here area decreases. So if dA is negative, decreasing area. So we call this as converging duct, or for a converging duct, what will happen? Area is dA is 0, and what will happen? This is dA is less than 0, that is negative, and this is positive, so dP will be negative, isn't it? So dP will be negative. Is it clear? dP is negative. Whatever be the sign for a subsonic flow, whatever be the sign of dA, that will be the sign of dP, simply. And the sign of dP will be just opposite. So dP was increasing in the earlier case, now dP will decrease and dV will increase. dV will increase. Now as dV increases, that means velocity, dV is positive, so velocity will increase, and this will be called a nozzle. And since it is subsonic flow, we will call this as subsonic nozzle. The nozzle means the velocity increases, and diffuser means velocity decreases. Subsonic nozzle. So here velocity increases. So case 2. Next, we will take up the second set of case where Mach number is greater than 1. That means supersonic flow. Okay. Now, for Mach number greater than 1, that means supersonic. Supersonic flow. So, what is that? Therefore, 1 minus ma square will be less than 0. So, that means 1 minus ma square will be negative. So, if 1 minus ma square is negative, now, therefore, the sign of dA and sign of dP will be opposite to each other. That means for a supersonic flow, the if the area increases, pressure will decrease. If the area decreases, pressure will increase. Okay, is it clear? Because supersonic flow means this is negative. So dA and dP will take take the opposite sign. Opposite sign. Clear? Hmm. Right. So now case 3. Case 3, that is dA is increasing. dA is positive. That means converging. I'm sorry, diverging. Ah. Diverging duct. Now, therefore, if dA increases, what will happen? dP will be decreasing. And always, if dP decreases, dV will increase. That is always true. This pressure and velocity are always in the opposite variation. Okay. That does not depend on whether it is supersonic flow, subsonic flow, convergent nozzle, convergent duct, diverging duct, etc. Pressure variation and temperature, pressure variation and velocity variation, they are always opposite. That must be understood properly. Okay. Next, we have basically area increasing. So here we have this is the direction of flow. Along this direction, area increases. So dA positive and Mach number is greater than 1. So dP will be what?
So negative.
dP will be negative and dV will be positive. So this is a diverging duct. So what we will call it? Nozzle or diffuser?
Diffuser.
Please follow properly. If velocity increases, we call it a nozzle. If velocity increases, we call it a nozzle. Here velocity is increasing. So we will call it a nozzle, not diffuser. Clear or not? Although you see that this is the geometrically they are same. But here it is subsonic and it is supersonic. So for a subsonic case, the velocity will decrease. But for a supersonic case, the velocity will increase. The same geometry, but will be acting oppositely for the subsonic and the supersonic flow. So we will call this as supersonic nozzle. Okay.
Yes, sir.
So it will be a supersonic nozzle. Supersonic. Why supersonic? Because Mach number is greater than 1. Supersonic nozzle. Nozzle. Why? Because dV is positive. So we will call this supersonic nozzle. Right? This is a supersonic nozzle.
Uh,
So we will call this a supersonic nozzle. Okay. Supersonic nozzle. Therefore, the remaining case, that is case 4, where Mach number is greater than 1, but area is decreasing. That means it will be a converging duct. So this is the diverging duct. This one is the diverging duct. So this is diverging duct. Next, case 4. So Mach number is greater than 1, implying that 1 minus ms square is negative and dA is negative, that is converging. Converging duct. So let us draw the geometry. So it will decrease. The area will decrease. And Mach number is greater than 1. So what will happen to pressure?
pressure will increase.
So area,
প্রেসারটা বেড়ে যাবে আর ভেলোসিটিটা কমে যাবে কারণ এরিয়াটা স্যার
area decreasing, so pressure will increase. Clear? Area is decreasing, so pressure will increase. Area is decreasing, so pressure will increase and velocity will drop. Velocity will decrease. Okay. Now this is a converging duct and it is supersonic flow. So what is the name of this duct? Therefore,
স্যার
hmm? See? What is the name of this duct, therefore?
diffusion duct.
Supersonic,
Supersonic diffusion duct.
supersonic diffusion, no, diffuser. Supersonic diffuser, huh?
Okay, sir, diffuser.
Huh. So it is a supersonic diffuser. Supersonic because Mach number is greater than 1. Diffuser because velocity is decreasing. Okay? Clear?
Yes, sir.
Okay. You can directly relate this term. So 4 cases must be crystal clear. Now here you see the dA variation with dP we have written. Now you can directly replace this dP with dV and you will get the variation of area with velocity. So let us write that. So therefore what is that? dA by A is equal to dP by rho v square. What is that? dP by rho v square. dP by rho v square is equal to minus dV by V, isn't it? From this, dP by rho v square is equal to minus dV by V. So here I will replace minus dV by V and 1 minus m square. So therefore, it will be minus dV by V 1 minus m square.
Well,
So from this relation also you can directly get the idea. Supersonic diffuser. You see that if it is supersonic, then this is always negative. And if it is negative, then negative minus negative, it is positive. Therefore, whatever be the variation of A, it will be the variation of V. So if area decreases, velocity will decrease. Clear?
sir.
So this is in terms of basically velocity. Earlier was in terms of pressure variation. This relation gives the variation of area with pressure, and this relation gives the variation of area with velocity. So we will mark this as another equation, equation 5. Okay. Okay. Then we will discuss in the next class the remaining thing. Any doubt regarding today's class or earlier classes? So let me just recapitulate whatever I have discussed today. So today I have started discussing on the one-dimensional isentropic flow. We have different variations of area, and accordingly we have different names for those variations. As area decreases, we call it a converging duct. If area increases, then we call it a diverging duct. And if we have a combination of initially decreasing and then increasing, we call it a converging diverging duct. So this converging diverging duct is called the de-level nozzle. As the engineer who designed this is a Swedish engineer called Carl G. B. Delaval. One thing that we have to keep in mind that you have seen Venturi also in fluid flow, but in case of Venturi, it is used for incompressible flow, and during the converging part, the velocity increases and pressure decreases, but in the diverging part, the velocity drops and the pressure increases. So that is for incompressible flow, but for compressible flow, the thing is different. So that is different. That means this is similar or in geometry to the Venturi in isentropic, that is in incompressible flow, but the actions are different from the incompressible flow. For a compressible flow, the variations will be different. Okay. Next, what we have seen is we wanted to see the variation of fluid flow velocity with area. That is fluid flow velocity, pressure with area. Now we had taken the mass conservation or the mass flow rate or the mass balance equation at different sections, and we differentiated and we got the differential equation which contains the variation of density, area, and velocity. Next, we have taken the energy conservation for the isentropic flow with no heat transfer, no work transfer, and no potential energy change. And we have got one relation between the pressure variation and the velocity variation. Next, we have combined this and got a relation of area variation and pressure variation by eliminating the velocity variation. You see that in both the relations, this one and this one, there is a velocity variation. So we have eliminated these velocity variations and got the relation between the area variation and the pressure variation. Here one thing we have done is del P del rho constant S is equal to C square, that is the velocity of sound square, that we have considered for isentropic flow. So the mass conservation is equal to rho AV at any section in the flow direction in the duct. At any section you take, I have taken say so many red dotted lines. So you see that at any section the mass conservation is, this is the means physical quantity. So rho into A into V. So A into V is the volume flow rate, and multiplied by rho, it gives you the mass flow rate. So this is mass flow rate that you know, continuity. Okay. Next, what we have done is we have differentiated both the sides, and dm dot is 0 because mass conservation, from the mass conservation, the mass is not changing. So the mass flow rate is constant. So dm dot is 0. Therefore, it is, you see that we have taken the differentiation of the product, just like xy, product xy or uv, the differentiation is u del v del x plus v del u del x. So in case of three quantities, it will be simply one quantity will undergo differentiation and all other quantities will remain unchanged. So that way we have got the differentials, right? Next we have done is divided by m dot on both the sides. And here it is m dot and here it is rho AV. Now you see that this AV and AV will cancel. Here with this term rho V and rho V will cancel. And here in this term rho A and rho A will cancel. Therefore, it will be d rho by rho in this term. dA by A, because all the quantities, other quantities are getting cancelled. So it will be dA by A. And here in this term, it will be basically dV by V, because you see that rho A and this rho A will cancel. Clear? So this gives you a differential equation including or containing d rho, dA and dV. Next, we have taken up the energy conservation equation. Energy conservation equation, you know, for isentropic flow without heat transfer, work transfer, and negligible change in potential energy, you know that H plus V square by 2 is equal to constant. So we have differentiated dH plus VdV is equal to 0. T, now you see that from the TdS relation, TdS is equal to dH minus VdP we know. Now for isentropic
sir.
flow, this TdS, this ds is equal to 0, and therefore dH will be equal to VdP. And since V is equal to 1 by rho, it is dP by rho. So we have got del P by rho plus VdP is equal to 0. That is the form of the energy conservation for isentropic flow without heat transfer, work transfer, and negligible change in potential energy. Okay.
Yes, sir.
Okay. Next, we have combined this and eliminated V to get a relation between area and pressure variation. And from this variation, we have replaced this del P del rho term, del P del rho at constant S, which is basically defined as the square of the velocity of sound. And from that, we have, since there is already a velocity of the flow square, that means velocity of the flow, so we have got the Mach number. Okay, so here from this relation, we have selected different cases like Mach number greater than 1 or Mach number less than 1. And accordingly, we have taken for each of these two cases, we have taken again area variation either positive or negative. Okay.
Yes, sir.
Next, we have got that how with area the pressure and velocity varies. For a subsonic flow, we have seen that for a diverging duct, the pressure increases and velocity decreases. This we will call a diverging or a supersonic diffuser. Because velocity is decreasing, we will call it a supersonic diffuser. And for this case, as area is decreasing, therefore pressure will also decrease and velocity will increase since it is subsonic flow. So it is called a subsonic nozzle. And for the second set of cases, when Mach number is greater than 1, that is supersonic flow. So Mach number 1 minus ms square negative. Therefore, if area increases, the pressure will decrease. And since the pressure decreases, velocity will increase, and therefore we will call it a nozzle. So we will call it a supersonic nozzle. Since it is supersonic flow and velocity is increasing, we will call it a supersonic nozzle. The opposite thing happens for the area which is decreasing. So it is a converging duct and the pressure increases and velocity decreases. And since velocity decreases, we call it a supersonic diffuser. And finally, we have got a relation, 1-to-1 relation between area variation and velocity variation, which you can study and confirm the cases, the variations or the relation between the area and the velocity. Okay,
Sir.
clear?
Yes, sir.
Okay, you please take notes. Okay, also. Okay, thank you.
Sir.
Then we are leaving. গুড নাইট। পড়াশোনা হচ্ছে তো ঠিকঠাক?
হ্যাঁ স্যার, পড়াশোনা
আর নোটটা,
মোটামুটি স্যার।
হ্যাঁ বলো।
স্যার মোটামুটি পড়াশোনা স্যার।
হ্যাঁ একটু ঠিক করে করতে হবে, সব সিলেবাস কিন্তু আছে, হ্যাঁ যথেষ্টই সিলেবাস বড় আছে, টাইম যা আছে পড়াশোনা করে নাও।